Good morning. Today we shall discuss a brief course in statistical mechanics. Why statistical mechanics? That answer you will realize the answer very soon. Physical system exhibits a large number of properties, and we want to understand the basics of these properties. And physics is trying to explain the reason for that. Historically, for a bulk system there has been different approaches, and traditionally it was the first approach is the thermodynamics approach. But thermodynamics cannot explain very many properties. It has its own limitations because it is a phenomenological theory. The thermodynamical relations are based on experimental observations, and a large number of properties can be explained based on that. But however, it has got its own limitations because physical properties are exhibited mainly due to the microscopic nature of the system. But in thermodynamics, it is not at all dealing with the microscopic state of the system. So, an alternative approach is needed to explain very many physical properties and also to predict many of the properties. So, it is in this context the necessity for another tool which takes care of the microscopic systems, and that is where statistical mechanics is relevant. So, statistical mechanics becomes a tool to explain the bulk properties of a system based on the dynamics of microscopic particles. How to begin with this problem? So, we shall start the problem like this. We will consider, or in thermodynamics you have realized a quantity which is called the entropy. Entropy has been used in many contexts to identify the physical properties, and according to the second law of thermodynamics, as you all know that entropy is maximum when it reaches to equilibrium. But a definition for entropy is not given in thermodynamics. You can only explain what is the change in entropy due to the change in heat energy and all these things. What is the absolute value of entropy? That is not given by thermodynamics. And here is this attempt given by great scientist Boltzmann to give an explicit expression for entropy. So, we will be starting with a concept which is called the statistical weight of a system. When we talk about a system which is a macroscopic system, we will have to define certain parameters or certain properties. So, we call a statistical weight defined as statistical weight omega of a macro state characterized by energy E, volume V, and number of particles. For a system with macro states, energy, volume, and N, let us define this is the macro state or statistical weight. This is the statistical weight. Statistical weight simply gives us the number of microstates that it is characterizing this macro state. That is the meaning of it. It is the number of microstates that compatible to the macro state. So, to begin with, what type of system we will deal with? We will consider a isolated system, totally isolated system. As you all know, for an isolated system, no interaction is allowed, so that energy is constant, and we have prescribed the volume as V and the number of particles in that. So, these are all specified, we know that. So, for an isolated system, I am characterizing the macro state as E, V, and N. for if the system is in when the system is in equilibrium, okay, this is the macro state. If that is not in equilibrium, other parameters will be there. I have to define other parameters, and consequently that parameter changes such that finally the system achieves equilibrium. But whole of this statistical mechanics what we are today discussing is based on the equilibrium or equilibrium statistical mechanics, or based on the equilibrium properties of that. When we talk about a system, we all know that the complete description of microstate is very complicated, because omega talks about the number of microstates. The complete description of a microstate is very difficult, because for that number of systems, very large number of 1 mole contain 10 to the power 23 particles. So if there are 10 to the power 23 particles, microstate means each particle will be having its own position, its own momentum according to classical mechanics. Whether you are using Lagrangian mechanics or Hamiltonian formalism, there will be coordinate and corresponding momenta in Hamiltonian formalism. So for 10 to the power 23 particles, it will be very difficult to handle with this number of states. So it's very difficult. How to handle that? In order to explain the physical properties, each and every microstate is not necessary. That is what the success of the classical statistical mechanics. Only the average properties are necessary. So the average, that is where the statistics comes in. With the average properties, you can discuss the macroscopic state. All we need to know is how many states are there that characterizes the macrostate. So the whole problem boils down to counting the number of microstates. So a macrostate, how many microstates are possible that characterizes this macrostate? How to count this? It's not a simple task, or in the hands of Boltzmann and Gibbs this has been successful. So we will try to look into see how we can calculate the number of microstates. That is what the main idea of calculating this statistical weight also. To give an idea, I will give an example. I will take an example how to count the number of microstates. Let us consider a paramagnetic substance so there are dipoles in it. And suppose if I apply a magnetic field, say, so each dipole will interact with the magnetic field. So and the interaction energy, as you all know, energy is minus mu dot B. Classically, all orientations are possible for these dipoles. But quantum mechanically, their orientations are limited. There are only finite orientations, and that depends on the angular momentum of these dipoles. So a spin half particles, for spin half, the angular momentum with h cross omega by 2, only 2 orientations are possible, plus half and minus half. So when we apply a magnetic field, depending on the strength of the field, if the strength is very high, they will be trying to polarize it along the direction of the magnetic field. Naturally, temperature, thermal effects will try to depolarize that, align the opposite direction, so that depending on the strength, there will be polarization. So if B is very high, all of them will be aligned parallel to the field, or depending on the field, some of them may align parallel to the field and some of them opposite to the field. So here now we will try to calculate what is the total energy or the macroscopic parameter of the system for an n particle system. So suppose there are n dipoles, such dipoles, and n dipoles are there. Suppose small n is the number of dipoles aligned parallel to the field, So this is a paramagnetic system having n dipoles, and I am assuming that let small n be the number of dipoles aligned parallel to the field. Then what is the energy? energy that's aligned parallel to the field, there are small n aligned parallel to the field, then the remaining n minus n is aligned opposite to the field. Minus mu b is the interaction energy, mu b is the interaction energy opposite to that. So minus mu b times small n, the energy aligned parallel to the field, the remaining n minus n dipoles are aligned opposite to the field, so n minus n times mu b. So that the total energy becomes from this expression n minus 2n mu b. Here mu is a constant. If I am applying a constant magnetic field, naturally energy is a function of only small n. That is why I have represented like this. E is a function of small n. Here that is the macroscopic state, that is the macroscopic state, the energy E. Now let us realize that all these dipoles are indistinguishable. When n is aligned parallel to the field, there are so many possibilities. There are so many possibilities. Let us look at the problem. Suppose n is equal to say 10, capital, there are 10 dipoles. Small n is equal to 2. 2 dipoles are aligned parallel to the field. Let us look at the configuration. 2 are aligned parallel, anti-parallel, anti-parallel, anti-parallel. Out of these 10, there is another possibility. There is another possibility. So there are different possibilities for being parallel to the field. They all represent the same energy. What we have seen it, we have already seen energy is n minus 2n mu b. So for the same n, here it is 2, so many possibilities are there. System don't know. We cannot find out the microstate. So all these possibilities are there. So that many microstates is characterizing this macrostate E of n. So the number of microstates. So in this simple problem, the number of such microstates can easily be calculated by the combinatorics. So that it is out of n, how many are aligned parallel to the field, NCN, which is equal to n factorial, small n factorial, n minus n factorial. You can easily calculate how many are. So if small n is equal to 0, if small n is equal to 0, which means nothing is aligned parallel to the field, or if small n is equal to capital N, all are aligned parallel to the field. Let us see, when NCN means n factorial, 0 factorial, n minus n factorial is 0 factorial, which is equal to 1. Only one state, all are aligned parallel to the field, only one state. All are anti-parallel, only one state. In between, if small n is capital N by 2, if small n is capital N by 2, so n factorial, small n by 2 factorial, n minus n by 2 factorial. For example, if n is equal to 10, small n is equal to 2, it is 10 factorial, n is 5 factorial, again 5 factorial, which means 10 factorial is 5 factorial becomes 6, 7, 8, 9, 10, 5 factorial becomes 5, 4, 3, 2, 1, 5 into 2, 10, 4, 2, 3, 3, so 42 into 6 divided by, yeah, that's right, 42 into 6, 42 into 6 you are getting 252. There are 252 possible states. There are 252 possible states for that. We are talking about 10 to the power 23 particles like that. Okay, so that number of such possibilities for a particular state will be enormously large. What we are realizing from this, when n is n by of the order of n by 2, it is the maximum. When n is larger than that, for example, if small n is 6, monotonically it will decrease. N is 7, n is 8, if you want calculates, it will be less than this 252. So it slowly monotonically increases, then slowly decreases till it will be maximum when n is equal to n by 2, then slowly it decreases. So that for n is equal to n by 2, it will be the maximum value. What does it represent? You have a large number of possibilities, right? It is very difficult to identify which is the possibility that is manifesting that, so that it is the totally random, maximum random state, highly disordered state. When n is equal to 0 or n is equal to capital N, it's the maximum order is there, right? Highly disordered state is when small n is equal to n by capital N by 2. So we can now relate this NCN to the statistical weight, because we said that statistical weight is a measure of, or it is the number of microstates. One can relate to n to this entropy, because this statistical weight to entropy. We can relate the statistical weight to entropy. Entropy is a measure of disorder. Statistical weight gives you the number of microstates, and if you think that for an isolated system that we are discussing, if there are so many microstates possible in that system, each state is equally probable, or all the states are equally probable. There are 10 states, 10 states are equally probable. So if you apply that condition, that is, if there are so many states, all these states are equally likely, then how the system will go to equilibrium? An isolated system will go to equilibrium. System will, according to the second law, this will go to equilibrium by extremizing or maximizing its entropy. Entropy is the maximum disorder, that is. So an equilibrium system is a system having the maximum probability. So that what is the maximum probability means the maximum value of omega, statistical weight. So statistical weight is maximum, already we have seen with respect to NCN. So omega can be related to NCN. So statistical weight is equal to NCN, and this is maximum, shows that it is there is maximum disorder, and entropy is a measure of disorder. So entropy can be proportional to omega. And here Boltzmann gave a definition satisfying the dimensional analysis, everything, because this has to be satisfied with the dimension of entropy. He defined it as this is equal to k log omega. This is the famous equation of Boltzmann, giving an absolute definition or an expression for entropy. Right? At a particular state, what is the entropy for having energy E, V and N, which is defined in terms of the statistical weight, k logarithm of the statistical weight. So one can calculate the absolute value of entropy, provided if we can calculate the statistical weight, which is nothing but the number of microstate that characterizes the macrostate defined by these parameters. So the whole problem in calculating entropy boils down to calculating the statistical weight. So the question is how to calculate. It is not as simple as we think about it, because when we talk about a large number of system, because we said statistical mechanics is aiming to explain the physical properties of a bulk system. A bulk system, 1 gram mole contains 10 to the power of 23 particles. So for 10 to the power of 23 particles to calculate the number of states, it is not a simple task. So there has been successful effort. So we will later on see that how to classically, on which approximation one can calculate this omega, and from that one can get this definition of entropy. And the advantage is Once you have this expansion of entropy, entropy can be related to other thermodynamic parameters, and through the thermodynamic parameters you can establish the equation of state, so that you can explain very many properties through the equation of state. That is the beauty of this equation. Now we can discuss the equilibrium properties of a macro system, and we shall derive some of the thermodynamic parameters using this equation. How we can do that? Let us see. Consider an isolated system which is in equilibrium. Macroscopic parameters are energy V and N. Let us consider it as two subsystems, 1 and 2, and their parameters are E1, V1 and N1. Other is E2, V2, N2, such that E1 plus E2 equal to E, V1 plus V2 equal to V, N1 plus N2 equal to N. So that is what isolated system is. Now the system is tending to equilibrium. There can be energy differences, so energy exchanges has to take place. Suppose this separation is permeable for energy transfer, energy will transfer from region 1 to region 2 or vice versa, depending on the distribution or changes in the temperature. So energy transfer will take place from region 1 to region 2. So let us see what is the thermodynamic or statistical weight of the system, total system. Already we defined statistical weight as so this is the statistical weight or the number of microstate that characterizes this macro state with parameters E, V and N, and a subsystem 1 with parameters as E1, V1 and N1. That is same as if omega 1 is the statistical weight of system 1 with parameters as E1, V1, N1, and omega 2 as the statistical weight for system 2 with E2, V2 and N2 as the parameters, because this is the number of microstates for the system 1 and this is the number of microstates for the system 2. That is the total number of microstates for the whole system, and for the subsystem it is the parameter E1, V1, N1. According to Boltzmann's definition, S is equal to k log omega. So if I take logarithm and multiply by k, so left hand side k log omega of E, V, N, E1, V1, N1 equals k log omega 1 of E1, V1, N1 plus k log omega 2 of E2, V2, N2, taking logarithm and this is. Now system at equilibrium means it is achieving equilibrium by increase of entropy. So if I look at how it is extremized or maximized, entropy is maximized. This is entropy according to Boltzmann's definition. This is entropy S of E, V, N, E1, V1, N1 equal to S1 of E1, V1, N1 plus S2 of E2, V2, N2. That is, entropy is something like an additive quantity. It has become as it is something like an additive quantity, because total entropy is sum of the entropies of the two systems. Now entropy is maximized with respect to some parameter. It is region from region 1 to region 2. If energy is exchanged, E is a constant, V is a constant, N is a constant. E1, V1, N1 are not constants. For that system it can. So entropy is maximized either with respect to E1 or V1 or N1. If you are saying that energy is exchanged, E1 changes. Suppose without changing the volume of the region 1 and region 2, or without interacting or without exchanging the particles from region 1 to region 2, keeping all these two constants, only allowing energy to exchange, entropy is extremized or maximized with respect to E1, keeping all the other constants V1 and N1. This becomes dou S1 by dou E1 plus, of course it is a function of E1, V1, N1 plus dou S2 by dou E1, V2, V2, N2. But this is with S2 is a function of E2, but E2, as you know, as we know that from this constraint, that is E1 plus E2 is E, E2 is E minus E1, so that this can be changed into dou S by dou E1 can be written as dou S1 by dou E1 plus dou S2 by dou E2, then dE2 by dE1. Of course here it is by keeping V1 N1 constant, here it is by keeping V2 N2 constant, dE2 by dE1. See, from this expression E1 plus E2 E2 is equal to E, dE2 by dE1 is minus 1, dE2 by d is minus 1, because so putting dE2 by dE1 as minus 1 there, this expression becomes, and according to second law it is maximized, which means it is equal to 0. System reaches equilibrium by maximizing the entropy, which means dou S by dou E1 should be 0, which means this expression is 0, which means dou S1 by dou V1 at constant V1 N1 is same as dou S2 by dou E2 at constant V2 N2. Now by defining this quantity as 1 by T1, naturally that is equal to 1 by T2. At maximum 1 by T1 is equal to 1 by T2, which means T1 is equal to T2, as we expect, because by exchange of energy, when it will reach equilibrium, when the temperature of region 1 and region 2 is same. So we have a definition for entropy here, dou S1 by dou N, though in thermodynamics we have, but there we cannot find out calculate the temperature from that, because there is not explicit expression for entropy. Here we have expression for entropy, so from that I can find the derivative and I can find out what is the temperature. So we have a definite expression for the temperature in terms of entropy, and that is the Similarly, we shall see that other thermodynamic parameters can also be obtained from using this expression, that is by extremizing the entropy with other parameters. So far we discussed with the energy, there are other parameters like volume. So if you are allowing volume to change and say asking when it reaches maximum, what is the thermodynamic relation between this, then we will get some other expression for thermodynamic parameters. Similarly, if you ask when n is changed, number of particles are allowed to change from region 1 to region 2, what happens when it reaches equilibrium? Then we will be getting some other thermodynamic parameters for region 1 and region 2, like that. So, all these thermodynamic parameters can be calculated in terms of entropy. That is one the great advantage, beauty of these expressions. So, Boltzmann definition of entropy S is equal to KL omega. From using S, we can calculate very many thermodynamic properties by demanding the equilibrium criteria, and using that thermodynamic parameters we can calculate the equation of state for the system. Yeah. So, what we have seen now in this session, we have understood using the expression for the statistical weight, which is the number of microstate for a macro state, which characterize the macro state. We have a definition for entropy as S is equal to K log omega, and for using the equilibrium postulate, we can calculate the expression for the temperature, which temperature is 1 by T is something like dou S by dou E with constant parameters of volume and n. Similarly, other parameters for pressure, chemical potential, etc., can also be calculated by demanding the equilibrium condition. This we will study in the next session. Thank you.